Hi, welcome back. This is another example of trying to figure out what a limit is when you know that the limit that you're trying to find, the value is a domain issue. So we have both of these two have that same exact scenario. So how do we deal with it? So um, very first thing is it's not a coincidence that you have a rational, we have a domain issue at two, and that's exactly where we're trying to figure out what the limit is. So the first thing we do, no matter what, we know we have a problem. We just got to figure out what kind of problem we have. And the two scenarios are either this is going to create an asymptote at this time or at this point, or it's going to create a hole. So how do we figure this out? So we plug into and we kind of see what we look like. So if we plug into, we're looking at having an 8 over an 8 on the top and a 2 minus a 2 on the bottom. So 8 minus 8 is going to get us a 0. 2 minus 2 is going to get us a 0. And that screams hole. If we have anything other than a 0 over 0, then that screams asymptote. We're going to take a different approach to that. But if we have a hole, that means that we have a common factor on the top and bottom that we can cancel away, which means we have an x minus 2 as a factor. So we're going to validate that very quickly because this is a difference of perfect cubes, and that means that's something that we can factor. So let's do a little bit of side work here. So we're going to take this and factor it. And if you remember how to factor this, we take the cube root of this and the cube root of this, which is going to be x and 2. And then we'll have a quadratic or something else with three terms that kind of make up the second one. So to get this first one, it's taking the first term times itself, x squared. The middle one is the combination of these two, so that's 2x. And then the last one is this one times itself, which is 4. And then our signs are dependent upon this original one. So our first sign is the same sign, and then it's the opposite, and then always positive. So this is going to be divided by x minus 2, and not coincidentally, we see that x minus 2 is a common factor. We knew that was going to happen because we had a hole, so we crossed them off. And now we're really finding what's the limit as x approaches 2. Because on a hole, remember, visually, the graph is moving along, you have a hole. And so that limit exists. We just got to figure out what the y value is. What should you get when you plug into, but we can't get it? Well, the only way we do that is cancel away this common factor and then plug it in. So we have x squared plus 2x plus 4. Now we don't have any issues. We'll plug it in. So we'll have 2 squared plus 2 times 2 plus 4. And that's going to be 4 plus 4 plus 4, which is going to get us to 12. So our limit as x approaches 2 is we are approaching the y value of 12. We'll never get there because we're not allowed to plug in 2 because it causes a 0 over 0. But we would be approaching a y value of 12. Right? We're going to do the same thing on this one. Not coincidentally, we're looking the limit as x approaches 10, and 10 ends up being the domain issue. But is it a whole kind of a domain issue? Are we going to get a 0 over a 0 on this? So same kind of thing. We're going to plug in 10 onto the top, save you a little bit of work. If we plug in 10 onto the top, we do in fact get a 0. And if we plug a 10 minus 10 on the bottom, we get a 0. So also screams that we have a hole, which also tells us that we are going to have a common factor. In fact, that x minus 10 is a factor. I just don't know what the other factor is. And so this is not a perfect cube, but I can take advantage of some other pre-calc college algebra types of stuff that I know that if x minus 10 is a factor, what I can do is I can take and do synthetic division with it. So I take the solution to this, which is 10, and I can divide it out, and I'll take my coefficients. So 1, negative 12, 15, 50. I'll drop down my 1 to start the process. And then we multiply, we add, we multiply, we add, we multiply, and we add. And not at all coincidentally, we get a remainder of 0. So if we were to divide out x minus 10 out of that cubic, you'd have left an x squared minus 2x minus 5. So what I'm going to do is rewrite it as we factored out an x minus 10. What we have left is the x squared minus 2x minus 5. And then that's going to be divided by our original x minus 10. And there's where our hole happens. So exact same scenario here. That's your common factor. That had to happen because of the 0 over 0. Now we're really doing the limit as x approaches 10 of x squared minus 2x minus 5. And so we'll plug in 10 squared minus 2 times 10 minus 5. And if we put all that together, we're looking at 100 minus 20, which is 80, minus 5, which is 75. So our limit as x approaches 10 on this original is going to give us a 75. We're approaching 75. We never can get there again because it's actually a point. It doesn't exist. It's a hole. How do we know we're right? Very quickly, very easily, we can go over to Desmos and take a look at this. Our original problem, here's our original problem, x cubed minus 8 divided by 2. Our limit was as x approached 2, we got a 12 out of that. So here's our original graph. It has a quadratic look to it. And there's the point that we would have gotten, but Desmos doesn't know to kick it out. The programming doesn't show you a hole in it, but that's the point we would be approaching. We just don't get there. And then if I go to our x to the third, this one, we're doing the limit as x approaches 10. We got 75. So this one, we got to zoom out a little bit. And there's that point. So that's the point on that graph. But again, the original, it doesn't exist on the original. As x approach 10, we got a y value of 75. So there's that point that doesn't actually exist. So hopefully that helps. And thanks for watching.